training large neural networks, especially large language models, is notoriously difficult. We rely on optimizers like Adam, but they can struggle with robustness, particularly when the loss landscape is noisy or highly non-convex. Newer methods like Muon introduce orthogonalization, aiming to stabilize training. However, these methods often exhibit dimensional fragility, meaning their orthogonalization precision varies significantly across different parameter dimensions, leading to instability. They're also susceptible to outlier-induced noise. A few very large gradients can throw off the entire optimization process. The core insight behind ROOT, Robust Orthogonalized Optimizer, is that we need both precise and dimension-robust orthogonalization and a mechanism to suppress the impact of outlier gradients. Think of it like this: orthogonalization ensures we're moving in relatively independent directions, preventing redundant updates and improving stability. But if some gradients are massively larger than others and point in bad directions, orthogonalization alone won't save us. We need to gently steer the optimization away from these misleading outliers. ROOT achieves this through two key mechanisms. First, for dimension-robust orthogonalization, it employs an adaptive Newton-Schultz iteration. Instead of a fixed number of orthogonalization steps, ROOT uses a Newton iteration, which quadratically converges toward an orthogonal matrix. Critically, it adaptively adjusts the coefficients within this iteration based on the specific matrix size being orthogonalized. This ensures consistently high precision across all parameter dimensions. Second, ROOT uses a proximal optimization framework to suppress outlier noise. This involves adding a penalty term to the gradient update that effectively shrinks large gradients, especially those that deviate significantly from the running average gradient. This biases the update towards directions supported by the majority of gradients, preventing the optimization from being derailed by single outlier events. The paper demonstrates that ROOT significantly improves robustness, converges faster, and achieves better final performance compared to existing optimizers like Muon and Adam-based methods. This is especially true in noisy and non-convex training scenarios, common in LLM pre-training and fine-tuning. By addressing the dimensional fragility in orthogonalization and effectively suppressing outlier gradients, ROOT offers a more stable and reliable training process. This means researchers and practitioners can train larger models, experiment with more complex architectures, and ultimately achieve better results, all while reducing the risk of instability and divergence during training.